From what? Lifting? Oh. You have weightlifting?
Did you know that today?
Oh, you go in the morning?
No, this is like, it's on Sunday.
What? Oh, you still share? You just went at it?
Because like, well, I lifted, you know, I went to go for basketball, so I lifted for that shit.
Because all of these are 2, then 1. I remember you saying that side should have 1. I don't know. Yep.
Wait, is that her?
The pattern is consistent. It matches with the
Oh, there's only 1 year because. How'd they make their flag? What's decorative?
Full flag.
Yeah, I like that. I like that one. That was tough. That one was from last year. That one, like, at our table.
I forgot to do the B1.3 quiz.
You can still do it.
Yeah, but it dropped it down from like a 98 to like a 90%.
You can still do it.
Yeah.
So what do you mean?
I just have to do the makeup quiz.
Oh, I thought, wait, he closed the quiz? Yeah. I thought he closed it like the end of the day today.
I mean, no. Now B1.2. Yeah. I got a 100 on the B1.
Oh, our test is next week.
Mr. Maynard. Mr. Maynard. Mr. Maynard.
What? Mr. Maynard. I don't speak He's busy. Understood.
You are not allowed to open my door, sir.
Trying to get you for like. We tried to get your attention for like 2 minutes.
Then walk over to me.
Exactly.
We knew he wasn't. But you are not responsible for the safety of our students. I am here, so I need to be the one. He is supposed to be here, that's true. But you don't know that. He has a cake.
You're next. That was dangerous, man.
Alright.
I also have to ask you for the quiz answers because I can't find one. For the answers. He puts the quizzes in.
Whenever he did it, did he have to pay money for this, or did the school give money?
I don't know. I know it was like Eagle Scout.
Yeah, I've seen that.
I miss the old benches. Yeah.
It's kind of pointless because you can't sit there walking into class.
No one's just there.
It's like, like before school.
Yeah, probably before school.
You can sit there during lunch.
Yeah, I think you're allowed to go like I know I think they changed it. I remember my freshman year sort of like we were allowed to go like to like other classrooms and stuff like that. But now now they like we're trying to turn it safe and all.
What? Down, up.
Hey, Will. Did you have to pay for, like, did you have to pay out of pocket for the little project? For the project? Oh, you raised the money. How much did you raise?
I want you.
How much?
I wish I took notes.
I lost my notes.
Martin's got notes.
Thank you. Yes.
I have history notes.
I'm not looking for history notes.
Yes. All right. After all this, this anybody for our dad joke for today, keeping with the Ice Planet jokes here. Did you hear about the snowspeeder pilot who downed an AT-AT? He was a real hot shot.
Brandon, keep joining
Hot
NHS.
shot. Hot shot.
Are you in NHS?
Yeah,
Join NHS.
I know. Some
I've done
days
the
are better than others.
We've submitted to that like M204 or whatever.
Okay. Into a grade.
What teaches that?
Alrighty, guys. So
Sounds
pretty
I don't know.
pretty short lesson for today.
School.
We are heading towards the end of our chapter. We've got one more lesson that's going to be on Thursday. Yes.
2 half-this.
Keep in mind, we should be working on our research plans because I believe our next due date for our IA is the 22nd, which I believe is Monday, if I'm not mistaken. Yes. So, what I'm expecting for the research plan, okay? I should have a basic procedure. It doesn't have to be like all thought out and everything, but think about what you're going to do for your IA. It should have like materials and things that you use to measure things. So you should be able to look at your paper and say, okay, I need to collect this, 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 and this. And then this is what I'm going to do to collect my data, to run my experiment. Keep in mind that you may, if you guys are making up a lab that you can share equipment, you can share equipment and that time that you're taking data, but each person should be collecting their own data and doing their own thing with it. So like, for example, 2 people who are building a circuit, okay? You guys can use the same circuit, but maybe one person changes something and then the other person changes something completely different. And so your things that you're changing and things that you're going to measure will be different, but you can use the same setup. So keep in mind that is a possibility, or you can just do it all by yourself. Also keep in mind that it could be a hands-on lab in terms of real life. You do the things in the lab. You can also use a simulation like Effect, things like that you can use a modeling software to do that, or you can do the database type project where you're collecting data from different websites and sources online, and then doing something with that particular data, okay? So, but what I'm looking for our next checkpoint, which will be next Monday, is a list of materials and a basic procedures, what you expect to do, okay? Which may change as you go throughout your experiment and you're like, oh man, like this really works, or man, this really doesn't, I'm gonna have to, change things up. So, things can change, that's okay. But if you are wanting to completely change your topic and research question and experiment what it is, the sooner you do that, the better, because once we start experimentation, then you're going to have to do a lot of that stuff over again if you're completely changing things. And I will not give you time in class to completely change things, that's on you. But you will have, so the week of homecoming, which is the first week in October, I believe, October 3rd is homecoming. So we'll have 2 B days then, and then the B day before that week, that'll actually be our first day of experimentation. So I'll give you 3 class periods total for working on your IA experimentation. If it doesn't take that long, then you can just use that extra time for analysis and starting your write-up and things like that, okay? But remember, the goal for this whole project, and I posted the dates online, so far those haven't changed, if we have storms that are coming within the next month or so, which it's been quiet, but I think the tropics are about to heat up here within the next week. So that may change. But the IA schedule is current as is. So right now that's the plan. So right now we should be thinking about and maybe asking me, hey, do you have these things in class? So that day one of IA experimentation, you'll be like, oh, do you have this? No, I don't. Oh, then I need to change what I'm thinking about. So try to, if you need stuff from me to check to see if I have something in class, try to do that before day one of experimentation. Okay? Because you don't want to wait too long and then you're like, you have less time to actually lab it out. Okay? Any questions on IA stuff? Sweet. All right. So we are moving right along. This chapter here, this B1, we are shifting into more of an astronomy aspect for today's lesson. We'll also talk about more astronomy stuff closer, probably right after Christmas when we do our E45, when we're talking about fission and fusion. And we'll talk in great detail about like life cycle stars and things like that. But for this time, we are taking the concept of black body radiation. We're going to assume that the stars are acting like a black body, and based on its temperature, it's going to have a particular brightness. But then there's the next aspect that says, okay, well, how far away we are from the star will change how bright it is as well. Okay, so let's look at our equation sheets, our data booklets here. Again, you're in B1, so let's go there in our data booklets. So we've seen everything up to this point. Remember that the brightness or the luminosity that we talked about, I'm not sure if that was last lesson or a couple of lessons ago, but our luminosity, our brightness here is L. That's going to be equal to that constant A times T to the fourth power. So we've talked about how our temperature in Kelvin, keep in mind, is raised to our fourth power. So the warmer it is, the brighter it gets a lot. Like we've got exponential growth here based on the fourth power. Okay, or maybe technically that's not exponential growth. That's I don't know, power growth, but you get the idea. The more change in or the higher temperature we have based on where we are gives us a great change of intensity. So let's take a look here. So they actually introduced to you the constant L with the special symbol here. So that is so the circle with a dot, that stands for our sun. So we're talking about, as we look at stars that aren't our sun, we're always going to compare the stars to our sun because that's the closest star that we have, and we can, do a lot of stuff with that. So this is going to be our constant. It should be in your constant part. Let's double check here. Although technically that particular part is not listed as being on the data booklet, but let's just double check just to be sure. Yeah, I don't see the luminosity of our sun here. We have a solar constant. Now that's interesting. So the constant down at the bottom here, that big S, okay, that big S is going to be 1.36 times 10 to the third watts per square meter. Is that the same thing as luminosity?
No. So
No.
the luminosity is in watts.
Well, I wonder. Let's play around with some units for a few minutes, okay? So, is this S actually L not here. So in our books, it doesn't say so, but I wonder how it's related to our luminosity here. So if we were to look at the Stefan Boltzmann constant, okay, so that's going to be in watts per square meter to Kelvin to the fourth power. Okay, so the area will be in square meters. The temperature will be, I'm sorry, that's Kelvin, and then that's Kelvin to the fourth power. Pardon. Mr. Maynard. Hello. Yes. Yep. Just kidding. At 2. Okay, cool. Yep. Alright. Low hit. Not yet, but you're going home at 2. Cool. Okie dokie. So if we were to cancel out our units here, so the luminosity will actually just be in watts, which makes sense because we talked about power, and originally it was a power equation which converted into this. Notice that this is, well, it's almost power. It's power per unit area. So the solar constant. So something has to be like power divided by the area to get to our solar constant. I wonder if that's going to come up sometime in our lesson. Well, let's find out. But in the meantime here, we have this L naught, or not L naught, the L of our sun is going to be that number 3.8 times 10 to the 26 watts. It mentions the luminosity of Polaris, which is, I forget, is that the closest star? No, that's Alpha Centauri, which is the closest star to us.
The North Star.
Polaris is the northern star, which interestingly enough, so if you can imagine like space, right? So we've got the Earth and we've got the solar system, and the Earth spins on its axis, right? So if we were to look straight up, we would find the North Star. Now, granted, we're not directly on the north pole here, but we are on the northern hemisphere. Technically, people in the southern hemisphere can actually see the North Star because it's on the other side of the Earth. Just like we can't see certain stars and constellations that Australia can see, like the Southern Cross and things like that. What was I going to that? Polaris. North Star.
Luminosity.
How can we see it from Earth? Cool, yeah. So, imagine, now, not sure if you know this, but the solar system is basically flat, okay? So most of the orbits of the planets are in the same plane. There's a little bit of wobbling up and down, but not so much. The biggest wobble is actually Uranus, or Uranus, whichever you want to call it. But if you look at the orbits of all of the other planets, then the Uranus orbit is kind of tilted like that. Okay, it's still kind of aligned, but it's definitely angled more than the other ones. So, but if you were to picture, okay, well, where in space is Polaris? All right, so if you can imagine, this is the solar system plane. Okay, so as we look up, what we would call as north. Okay, that would be like up in space through the Milky Way galaxy, looking at all of the other stuff up there. And so Polaris happens to be up here instead of like over here or over here or down here. Okay, let me get my door and then I'll talk more about that.
Black holes.
Hello?
It would speed up.
Fun! You are wanted to answer questions
I forgot Fun was in here.
for the yearbook,
He's on the swim team.
if you so choose.
But It's the black hole would speed up the light. So like, pretty bright,
Would black hole speed up the light?
I guess. Shatter.
So yeah, I don't know really where, like, what the end result was, just to kind of give you a picture of where in space things actually are. It has, so I saw some things recently that that made mention of the fact that our solar system is really far away from everything else. It's almost like there's a bubble around our solar system compared to everything else that we see, which is kind of interesting. Some people think that we're actually living inside a black hole. I'm not sure if I would buy that or not, but it's interesting to read about it. People are talking about it, so that's cool. Of course, just because it's online doesn't necessarily mean that it's true. So we all have to take it with a grain of salt and check our sources and things like that. But yeah,
Do you know how black holes
interesting
form?
stuff.
How they form.
So let's talk about luminosity.
Star?
So
Star?
remember the luminosity or the brightness. No, sorry, I can't. So it's easy to equate those, but you cannot. And I'm glad that I made that mistake myself, because you guys are going to do that too. So brightness and luminosity are not the same thing, okay? The luminosity is the power output of a star. So based on its temperature, it's got a particular luminosity. You could say brightness, but we have to be specific. It's brightness if you're on the surface of the sun or the star or whatever it is that we're at, okay? If you are a distance away, the luminosity still stays constant because that's the power output of the star, okay? But the brightness depends on how far away you are. And it really, so imagine we have the star, right? So here's the star, our sun, whatever. And so it is pumping out a certain amount of watts per second, okay? So based on the luminosity of our sun, our book tells us that it's about 4 times 10 to the 26 watts. That's a ridiculous amount of power, okay? And again, power is going to be the rate at which it expels, no, wrong word. Outputs, I guess, is the best word that I can think of right now, or that you can think of. But remember, power is going to be the rate at which the energy is being put out, okay? So the greater the power, the greater the luminosity, the more output the sun or star is giving out, okay? So we can say more EM waves are putting out per second, and more intensely and all of that stuff. So more sunlight, more EM waves, if we've got more power. But, so imagine that power goes in all directions. So like a light bulb, once you turn it on, that light goes in all directions, right? It's not like it's inside a flashlight where it's directed in one. So the star, because there's nothing to block it, so light goes in all directions. So imagine the energy as a shell. And that shell is expanding, kind of like a wave, right? If we drop a rock in a pond, or we stick our finger in the pond and we make a wave, okay? That initially has a particular amplitude based on the energy of our wave, but it's going to spread out over time. And as it spreads out, the energy that it initially had, which was a large amplitude, now it's all spread out as it gets bigger and bigger and bigger. So use that same concept when we're talking about the sphere of sunlight. As that expands, it's the same amount of power, but spread out over a large distance. In fact, if we were to say, okay, well, it's spread out based on the surface area of that sphere of light, let's say, okay? So remember the surface area of the sphere for pi r squared, where this r is going to be the distance from the star, okay, out to wherever we are observing it. Like if we talked about the how bright our sun looks like from the Earth, okay? Compare that to how bright our sun is from Mars or Venus or any other planet. The sun's luminosity stays constant, but the brightness observed from our different planets, because we're different distances, is going to be different. Shadow.
So that are the distance from the sun, I say the sun, from the star to the Earth. That's the same as the D in the booklet for
Yes.
apparent brightness? Okay.
Yep.
So, it's, okay, I wasn't sure about that.
Yep. So we have our next equation here, which here it is. So in our equation sheets, our only equation that we actually have for today here in our B1 is that brightness equation. So if we take the power, which the power of star, we call that luminosity, and we divide it by the surface area of that the sphere of light as it expands, then that's going to give us our brightness. So notice though that our brightness is going to be in terms of watts per square meter. Hey, the solar constant is watts per square meter. So the solar constant is in fact the brightness that we observe on the Earth. Now, if we were on Mars, then that would be different, because Mars is going to be further away. So the brightness, the sun is not as bright on Mars as it is on the Earth. I wonder, and we would have to look up some numbers, but I wonder if it would be safe to view the sun with your naked eyes on Mars. Because we know that we can't on the Earth, right? If you stare into the sun, you can cause your damage to your eyes. That's why when there's a solar eclipse, we always have to have those special glasses. I don't know when the next one is. I know we had one last year?
No, I think what, maybe?
Or maybe this spring. It was in April something? I don't know. I wasn't close enough that it actually made a difference.
September.
But I don't think that we're going to have one in the United States for a while. It might be like another 7 years or so. I don't know. It's weird. Martin.
So is S just the brightness of the sun that is the observed brightness of the sun here on Earth?
Yes.
Okay.
Precisely.
Okay.
Yeah.
Mr. Mayor.
Yes.
It looks
Maybe
like
the
the next
distance?
solar eclipse.
Yeah.
That's gonna be observed in the US is gonna be in August of 2044.
Wow. That's a long time. Interesting. So, yeah, that's what, 2 more years? 19 or 19, yeah.
For
yeah.
what, a total solar eclipse?
19, yeah. Well, that can be seen from the US. I'm sure that one happens sooner, but you'd have to go to a different part of the Earth
Yeah,
to see it.
Jacksonville's August 12th, 2026
Wow.
for a total.
What? Wait, what?
August 12th, 2026 total solar eclipse from Jacksonville.
Really?
What's your source?
Google. It says NASA Science.
NASA
I don't know.
Yeah. So a purpose says that the next one will be next year.
I should search it up. It just said that one.
Oh, wait. How? No, what I'm seeing is that next year.
Am I wrong?
Okay. So he said that
Same thing.
the next one next year will happen in Europe. Can you confirm?
The internet.
No?
Looking at
All right.
the AI
Well,
overview, Brad.
we'll talk about it
It
later.
doesn't work?
Alright. So we've got our brightness equation here, and this actually comes from, let's see if we can isolate, I know we talked about intensity before. Intensity, let's see, it's not here in the B.
C.
It's here, let's see. C? In our C chapters, intensity?
Nope.
Do we have intensity over here? No. It's not D for fields.
They went over it.
Yeah,
in the notes.
yeah, we definitely went over it, but it might not be an official equation given to you on your data booklet. Yeah. Intensity, no, not there. We got pressure.
We're going to the intensity equation.
Yeah.
Yeah.
Okay. So
I wanna
we've got our
read
brightness
it
here.
later.
So
This
the main
intensity
thing
one?
that we have to
Yeah.
understand here is that our right, it's just like the force of gravity, just like the Coulomb's law equation, that it is an inverse square law. So if we have something twice the distance away, then our brightness is 1/4 as big. So, and then let's see, there were some other things that we had to talk about. So we talked about intensity. They give you a neat little picture of the spreading out on page 200. And then they give you a relationship here that the intensity is inversely proportional to the square root of our distance, but that's nothing new here. They also include, so if you look through all of the pages here in your book, you'll also see that they occasionally give you some math tools. So in this particular case, they have a little short lesson or reminder on how to make a graph look like a line. Okay, so we talked about that in great detail. We did that a lot with our labs last year. And as we're heading into the papers at the end of this year, in your paper 1B and your paper 2, those are all short answers. Some of them might have graphs on them, especially the paper 1B, okay? Because it's going to be heavy on like the data analysis, the graphing, the uncertainties, that sort of thing. So they may ask you to, graph something in such a way that it would change from one particular type of graph into a line. So just a reminder of, we really just have to look at what our equation says, and what our equation says is what we need to do. So that's a good reminder of us. They also talked about astronomical distances, like candles and other things, but we'll actually come back to things like parsec and light year in the future. So we don't necessarily need to do that right now, unless, as I look at your pods, I don't think that they are using things like parsec in light years at this point. That'll come later. But this is kind of like the intro to that. You sure? Yeah, go ahead. Sign out, take the bath. All right. Any questions for the good of the order? All right. I told you that it was a short lesson for today, so you can jump into your pods. Next class will actually cover heat. So two equations for heat, one of which will change the temperature of the object, but it will also talk about phase changes. So that's fun too. And that'll wrap it up. We should have, it's been in the copiers for a few days, so hopefully we can have your review guides by Thursday as well, so that you guys can do that. And then as we head towards next week, Monday will be our next lab for the HLs. SLs, you guys get to just study on your own, work on your review guides, and then next Wednesday will be our test on B1. Alright, so that's the plan. Of course, keep in mind on Monday, when we have our lab for our HLs, that's also when our IA research plan is due. So SLs, if you didn't get it done by Monday, you could actually work on it in class on Monday and turn it in at the end of the day. Cool. All right. Feel free to take 5, and then we'll jump into our pods. There is no quiz for today because it was so short. I am combining because there's only like 3 questions that I could actually find. So I'm combining this lesson with the next one to make us a full 10-question quiz. Okay, so no quiz for today. Combined quiz for next time. But that does mean that if you get an A on the quiz, then that'll cover both pods, like we might have seen before.
Right.
Okay?
Okay.
Cool. So take 5 if you need to.
Oh my God.